Alright, last problem that I'm going to do from this section. So there is actually a diagram down here that is really important for this problem, so I actually decided to draw it out. Admittedly, this is really going to be confusing to deal with all these windows, but hopefully it won't be too bad. So we take A as the integers, M is Z mod MZ, N is Z mod NZ. Determine the necessary and sufficient conditions for two short exact sequences to be isomorphic. Of course, E alpha and E beta. So this is what E alpha, this one is E. Okay, fine, I have to go back to here. E alpha, E beta. So those are the short exact sequences that we're dealing with. And this is kind of tricky, but if you start from E alpha and E beta being isomorphic, you end up with some weird looking condition down here, and it ends up being exactly what you want. So, if these are isomorphic, what does it mean for two short exact sequences to be isomorphic? That means that if we have, let's see here, so we'll call this F alpha and G alpha and F beta and G beta because they correspond with E alpha and E beta. So we have this map phi that goes from P alpha to P beta. And phi is an isomorphism. And then if we look at these two sort of squares here, we got this one here between the M's, P alpha, P beta, and one here between the P alpha, P beta, and the N's. Now both of these squares have to commute, i.e., if we start at M and we go through F alpha and then through phi, that's got to be the same thing as going through F beta. I.e., F beta is equal to phi composed with F alpha. And then similarly for this diagram, if we start at P alpha and go to N through G alpha, that has to be the same thing as going through phi and then through G beta. I.e., G beta composed with phi needs to be equal to G alpha. And that's exactly what I've written in the first 2.5 lines here. Now, let's say that P alpha is generated by E1 and E2 and P beta is generated by E1 prime and E2 prime. Then we've proven that like F alpha, like the F's and the G's have certain properties, i.e. F alpha will send 1 to E1 and F beta will send 1 to E1 prime. Then, and that's sufficient because M is generated by 1. And so, because of linearity, we've defined it on the whole set. Anyways, after that, G alpha of E1 and G beta of E1 prime are both going to get sent to 0. And G alpha of E2 and G beta of E2 prime are both going to be 1. So, let's see here. So, we know that phi of E1, well, that's phi of F alpha of 1, because F alpha of 1 is E1. But because this diagram commutes, the first square at least, because the first square commutes, phi of F alpha is the same as F beta. So this is equal to F beta of 1, which is E1 prime. So therefore we know that phi of E1 is E1 prime. And so we've been able to conclude that just from knowing how this diagram commutes. What else can we conclude? Phi of E2 is, well, we don't know where it's going to go yet, but we know it's going to map to some linear combination of E1 prime and E2 prime. So let's say it's A times E1 prime plus B times E2 prime. And of course here A and B are integers because what we're doing is, this is the, P beta is in a abelian group generated by E1 prime and E2 prime. So it's all sort of things that you can construct using E1 prime, E2 prime, E1, and also negative E1 prime and negative E2 prime. And so if you just add it and subtract, if you add those and subtract those from themselves some number of times and bring all the E1 primes and the E2 primes together, you get some integer multiple of E1 prime plus some integer multiple of E2 prime. So anyways, so we want to know what A and B are. Well, so your 1 is G... Shut up. I'm also no way am I waking up at 7:30. So 1 is G alpha V2. We know that by construction. But G alpha is G beta composed with phi. And so phi of E2, well, we know is just this thing. And so it's G beta composed with A E1 prime plus B E2 prime. But because G beta of E1 prime is 0, this is just going to be B. Because what's going to happen is, because of linearity, this is just going to be B times G beta of E2 prime, which is just B times 1, which is B. So what do we have here? We have B equals 1. Therefore, phi of E2 equals A times E1 prime plus E2 prime for some integer A. So now, using these facts, we also know that phi is an isomorphism. Therefore, 0 is phi of 0. Now, in P alpha, we have the relation n times E2 equals alpha times E1. So therefore, phi of 0 is phi of n E2 minus alpha E1. Then we use linearity. And then phi of E2, now we have a formula for it. And then we multiply it out. And now we know n times E2 prime is equal to beta times E1 prime. So we do that substitution. And now this becomes na plus beta minus alpha E1 prime. So therefore, na plus beta minus alpha is congruent to 0 mod m, because this equals this mod m, or 0 equals this times this in P alpha, in P beta, and since P beta is generated by E1 prime is not going to be 0. Or, well, that is one thing that I really thought about, like, what if E1 or E2 are 0? And I think what happens is that if E1 or E2 are 0, like, it's just stupid. The problem just doesn't really make sense and things are sort of dumb. So I think we sort of implicitly assume that E1 and E2 are non-zero. Because otherwise it doesn't really make sense to consider an abelian group generated by those two things. So I think we sort of implicitly assume that those two elements are non-zero so as to make the problem, like, interesting. But, I mean, I could be wrong, but if I'm wrong about this, then there's probably just, like, another sentence that you have to say, like, oh, if E1 is 0, then things turn out to be sort of dumb, and if E2 is 0, then things also sort of turn out to be sort of dumb. And so it's not like a huge deal, really. Really, the interesting... You start to get a sense of where the interesting stuff is happening. And the interesting stuff is happening when E1 and E2 are non-zero. So even the relations themselves are sort of, like, dumb. Like, n times E1 equals 0, well, that's obvious if E1 is 0, and it's not even interesting to say that. But anyways, enough ranting. So na plus beta plus beta... Okay, so anyways, E1 prime, we're going to say it's not 0, so this thing is 0, and this is 0 in... Where are we? We are in... Where are we? Oh, wait a minute. Oh, yeah, okay, so let's backtrack on everything that I said there. What we're really using here is that, m times E1 prime equals 0 in P beta. So, we're not even worrying, it's not like, oh, multiply two things together, get 0, that means that this thing is 0. That's not what we're using even. We're not even worrying about that. What we're using is the fact that, E1 prime times m equals 0. So, if E1 prime times this equals 0, then because E1 prime... Okay, so I guess we're using E1 prime as non-zero because if the fact that E1 prime times m equals 0, and that's the only relation that can sort of kill E1 prime, implies that this thing here is going to be a multiple of m. Because the relation, or the fact that we're taking a group generated by E1 prime and something else, and also impose, the only relation that kills E1 prime is that m times E1 prime is 0, that means that if you choose any integer less than m, strictly less than m, then that integer times e1 prime will not be 0. Because there's no way to force that, given that it's just a group generated by this thing. So anyways, so this thing here has to be some integer multiple of m, which is to say that na plus beta minus alpha is congruent to 0 mod m. Therefore, there is some element a in PA. Okay, so I guess, yeah, well, is it in PA? Well, we're writing this element, so it really should be in, it should be an integer. It should be in Z. Some a in Z, some integer Z such that na plus beta minus alpha is congruent to 0 mod m. And it wouldn't really even make sense for this to be in, for it to be in P alpha. If anything, it should be in P beta, since E1 prime is in P beta. But yeah, it's all these things, these are all integers, so it wouldn't even make sense for it to not be an integer. Okay, so I was right. So, well, I was right when I was saying it, not right when I was typing this up. So there's some integer a such that na plus beta minus alpha is congruent to 0 mod m. I think there's another way of stating this that involves, like, congruent to, like, maybe beta minus alpha is congruent to 0 mod d, where d is the greatest common divisor of m and n because we got this n here. It's something like that. And that might be a little more straightforward, because that, I guess, would sort of tie it into, like, you would expect there to sort of be something going on with some special relation between m and n, like maybe involving their greatest common divisor, because one of the other previous problems involved the greatest common divisor. But, like, you could write it out using that, but you don't need to. This is whatever that thing, whatever potentially nicer formula there is for this, it's going to be equivalent to this, because this congruence, this is all you need to prove the other direction, and so this is the equivalent, is the necessary and sufficient condition, or in any sense, it's equivalent to any necessary and sufficient conditions that they might otherwise be looking for. Okay, so for the converse, and this is, it's trickier to come up with this proof, but once we get to here, we can sort of think, oh, well, if we knew this, would we be able to go the other direction? And it turns out you can. So there is some, suppose that we have the short exact sequences E alpha and E beta, and we know that there is some integer a such that na plus beta minus alpha is congruent to 0 mod m. Now we can prove that there is a phi which makes these two diagrams isomorphic. So define a map phi from P alpha to P beta by phi of E1 is E1 prime and phi of E2 is AE1 prime plus E2 prime. Extend the domain of phi from this to all of PA linearly. The resulting function is well defined because, let's see here, in P alpha, any E2 equals alpha E1. So now here, phi of n E2 minus alpha E1 is going to equal what? How did I get here? Oh, I basically, like, the equation here, the way you get from here to here is identical to going from here to here, because the only things we use here are linearity of phi and NE2 prime is equal to beta E1 prime, and those are things that we already know, so we're allowed to use them. So phi of this equals 0. I should probably put in there, like, by the computation from the last paragraph, just to make clear how I'm going directly from here to here. It's really just because I didn't want to repeat all of this. Anyways, so this is equal to 0 because this is congruent to 0 mod m, and because m times E1 prime is 0. And so therefore the relation NE2 equals alpha E1 is preserved under phi. Because phi of this equals 0, that means that yeah, so NE2 minus alpha E1 right, because if NE2 minus alpha E1 was not mapped to 0, then it wouldn't be well defined. So therefore this so I guess we don't really I don't think this sentence really this part really makes sense, that the relation is well, it's sort of preserved in the sense that like if you apply the relation, then you're not going to change the answer. But I think this might be like an awkward way of phrasing it, so it might just be best to say the resulting function is well defined because of blah blah blah. Alright, so there's that. To prove that phi is bijective, let's define an inverse function. So we'll go psi from p beta to p alpha by psi of e1 prime is e1 and psi of e2 prime is minus ae1 plus e2. And extend this linearly, blah blah blah. Then what happens? Psi of ne2 prime minus beta e1 prime. What are we doing? Well, define this. So here I actually redid the calculation because we hadn't done it in the other direction. But it's basically the exact same calculation. You just replace you flip the primes and the not primes and some other stuff. You flip the phis with the psis and it works. And importantly, you get this minus e1 times this thing, and so it's going to be minus some multiple of n times e1, so it's going to be minus something times 0, which is 0. So anyway, psi is well defined. I'm going to erase that again since I don't think it's well phrased. Furthermore, what happens if you compose these two things? Psi of phi of this thing, well, phi is going to use linearity of phi, and then phi is going to send e1 to e1 prime, and phi is going to send e2 to ae1 prime plus e2 prime, and then you bring the psi e1 prime terms together. Here we're using linearity, and here we're using linearity. Now if you multiply this out, this becomes e1, and then this becomes this, and then the yae1 will cancel with the minus yae1, so all we have left is xe1 plus ye2, and that's what we started with, so psi is the inverse of phi, so phi is bijective, therefore phi is an isomorphism. Okay, so phi is an isomorphism, that's good. Now all we need is commutativity of these boxes, and for that we have f beta of 1 will be e prime, but that's equal to phi of e1, which is phi of composed with f alpha of 1, and since 1 generates m, f beta is equal to phi of f alpha. Now, here g alpha of e1 is 0, which is g beta. Oh, that kerning is really bad, but I wanted to line them up in some way, so I had to. So 0, but that's g beta e1, which is g beta of phi of e1. And then for e2, this is 1, this is a g beta, this plus this because, you know, the thing, because it's g beta of a e1 prime plus e2 prime, right? Because that's, oh, no. The reason, so this is the easiest thing here is to actually go backwards through here. So g beta of phi of e2 is g beta of ae1 prime plus e2 prime, because that's what phi does. And then that is equal to, well, the g beta of e1 prime is 0, so this term will drop out, so all we're left with is, oh, no, I lied. So this is going to become alpha g beta e1 prime plus g beta e2 prime. Oh, but yeah, so now this term will drop out because g beta e1 prime is 0. then G beta E2 prime is 1. So really how I actually did these was I started from here and went to here, started from here and went to here, started from here and went to here, and then I started from here and went to here, I started from here and went to here, then I started from here and went to here. And once I confirmed that I got at the same things from, let's undo that. I got at the same things from both directions, then I could write out this string of equalities. Just to make it clear that you start at one thing and end at the other thing. But this is just one of those typical examples of the way that you write out the proof is not the same way as you come up with the proof. But anyways, so we have, because 1 generates m, this holds, and because E1 and E2 generate P alpha, we have G alpha equals G beta composed with phi, and thus that's all we needed to prove that E alpha and E beta are isomorphic, and now we're done with the proof, and yeah, that's it.